creates, through Bernoulli's principle, it creates a low pressure on top, and the below naturally pushes it up, so you get lift. Okay, so that's how you can get lift. And then what about thrust? Well, you get thrust in an airplane from a jet engine. Okay, you don't get thrust from the airfoil wing. You get it entirely from the engine, and you don't get lift from the engine. You just get a big force pushing you forward from the engine. Okay, so they're not coupled. Okay, and then your last thing is you want to achieve steering. Well, airplanes achieve steering by lifting up flaps and ailerons, so that when the wind hits it, the aircraft can steer. And again, those things don't help you achieve lift or propel you forward. Okay, so they're all independent, and so if you multiply this, you can see design parameter 2 and 3 don't influence FR, just DP1, and vice versa. FR2 is only influenced by DP2. Okay, and he would say that's desirable in axiomatic design, to think about design in this way. Not only identify your functional requirements and design parameters, but make them uncoupled. And the reason is because it keeps things simple. If something breaks, if one of these functional requirements don't work, then you know exactly how to fix it. You know which design parameter. You can imagine if they were coupled, if there were numbers, or if these weren't all zero, if they were different numbers, then all three design parameters influence each functional requirement. Then, if one functional requirement doesn't work, you have to tweak all three design parameters. Those may change and break the other two. So you don't want things to be coupled. So by the way, another great example of this is in showers. Low-end showers have two knobs. One knob is for cold and the other knob is for hot. And as you turn them up, they both increase the pressure. And that's bad because, gosh, you might tweak those and get just the right temperature you want, but it might just be dripping out. You want higher pressure, you turn one up and suddenly it gets too hot. And so it takes immense amounts of trial and error before you get the right pressure and temperature. So, because it's a coupled design. The functional requirement to get pressure and to get temperature are coupled by the two knobs, right? The design parameters that get the two knobs. And so, higher end showers, you just have one knob that only independently controls pressure and another knob that only independently controls temperature. So that way you can fix one and then do the other without influencing it, right? So it seems that with all these examples, you start concluding like, yeah, you want to not only identify functional requirements and design parameters, but you want them to be uncoupled. You want to keep things simple and independent, and that makes for good design. And that's held for centuries. The humans have used this for as long as humans have been around, to make good designs that are just simple. And so this is why we kind of went down this path. But then you look at nature, and it totally breaks all the rules. Not only is nature highly complex, it doesn't keep any design simple, but it's massively coupled. So you look at a bird, how it achieves the same three functional requirements. Well, it achieves lift, thrust, and steering by flapping. So yes, they have airfoil wings, but they also achieve lift by flapping. They achieve thrust by flapping, and they achieve steering by flapping and moving their wings. And then think of a snake. I mean, the darn thing's just a cylinder of muscle, and it does everything. It hunts, it climbs, it moves, it strangles, it digests. It does everything with just that simple cylinder. And so it's heavily coupled, right? So this is why we didn't follow nature. It was just too complex for us. It's not clean and independent, and we generate designs that we couldn't handle. And I mean, think about this. Like, if, say, you wanted an end effector to move in a certain path, like, say, just in a nice circle. So you wanted this point here to go in a nice arc about the center here. Well, that's super easy to design if you make it rigid. You just make two rigid parts and put a pin joint there, and you're guaranteed that it will continuously rotate exactly how you want. And it doesn't matter what material this is made of. This could be steel, copper, aluminum. It doesn't matter as long as it's both rigid. And you can almost push on it anywhere you want, however you want, at any time. And no matter what you do, independent materials and direction and how you push on it, it's going to rotate around this point. And, and if you want to add compliance, just put a torsional joint there to independently tune the stiffness. Torsional spring or something. So that's why everyone went down the rigid path. But you can imagine, if you have a compliant piece and you want this to move in an arc, well, this gets much more complicated because, first of all, it becomes a very highly nonlinear problem. Once you deform it a finite amount, everything starts changing, and this moves in a very non-circular way. It can be approximated by a circle, but knowing where the center of that circle is and how that moves is very complex, and it's dependent on where you push on it, how you push on it, and how you keep pushing on it over the deformation, and what material it's made of. So it's just highly coupled, highly nonlinear, very difficult to figure out. Okay? So this is why I think humanity was like, okay, we don't even want to deal with this. We're just going to go do things rigid and keep things simple. And so has design been for ages. But now, with the advent of new design tools and professors like me whose vision is to make the design of compliant things easier so that you can use the compliance and mimic nature, you can get much superior designs that are, yes, coupled and more complex, but have huge payoff in their performance. Okay, so let's look at some compliant mechanism applications. Okay, again, this is another one from Larry Howell's group. It's a chainsaw clutch. Okay, the way chainsaw clutches traditionally worked is that they're made of 3 different pieces, 2 rigid pieces and a spring. Okay, and it's attached to kind of the motor here. And of course, when you pull the cord on a chainsaw and you get the motor going, that would be really bad if immediately the chain started moving, because it's really hard to hold it and keep yanking the cord and finally get the motor going. And it might be by your foot or by your hand. You can cut yourself in a very serious way. So you want the motor to turn on and not have the chain move until you are ready, you're holding in place, and now you pull the trigger. And then when you pull the trigger, you want the chain going. So the way this works is once you turn the motor on, this guy's rotating around the center here. Say it's that. It's just moving around like this. But it's going slow enough that the centripetal force doesn't pull this out enough to engage the chain. But then when you pull the trigger, you give it more gas, this starts spinning faster, and the centripetal force will pull those, centrifugal force, will essentially pull this out and engage the chain, and then the chain will get going, right? So, and by the way, so of course this is 2 pieces connected by a spring, or 3 pieces. And Larry Howell said, hey, let's make a compliant version that's lighter weight, easier to make, and is a single piece. And here's 2 different designs. He has a video of this one. This one is, let's see if we can get this to play. Okay. This design is actually 2 pieces. The green piece is the compliant piece. The blue piece is stuck to a motor, and the orange piece is the outer sleeve where the chain would be attached. And you could see, if you rewind the video, you'll find when it initially begins to rotate, the green piece doesn't have enough centripetal force to pull it out, and it doesn't engage the orange part until it's sped up. Okay, so that's how that works. Okay, another neat compliant application is made by having these 2 cylinders that are connected by just a straight flexure strap. And if you make 4 of these and position them in alternating ways, okay, and then put like pins through there, and then deform the straps in place and put pins through there, now you get a very interesting compliant joint that is extremely stiff in all directions. If you crunch it or stretch it or shear it or anything, it's very stiff, but it can rotate almost 360 degrees in either direction. This design, depending on how you design it, could flip 360 degrees back and forth with almost no stiffness. And it's really remarkable because most compliant joints, they're limited in range, And as you deform them, they increase in strain, and they start getting to yield strength, and they break. Well, as you deform these in place, they reach some stress that's below their yield strength, but then no matter how much you rotate it, independent of its position, that it never increases in stress, internal stress. It never approaches its yield stress because the curvature on the strap, whether it's wrapped around this drum or that drum, is the same. So over its entire range of deformation, almost 360 degrees, unheard of by a compliant hinge, it doesn't ever increase in stress, so it doesn't break. And it also remains the same strain energy, which means the force to resist it, which is the derivative of the strain energy with respect to the position, right? The displacement, that essentially is zero. And I know that's impossible. It's impossible with a zero stiffness joint. And in truth, to assemble this, you need to stretch these straps a little bit to hold it firmly together. And once you stretch it, you do add some stiffness. But theoretically, if you were able to make them the perfect length and assemble it without anything going wrong, these would have zero stiffness. So you can get zero stiffness joints that are very stiff in all unwanted directions and move 360 degrees without breaking. So these are used all over in compliant in robot joints and all sorts of things. So always consider using these. And they enforce rolling contact motion. So they're basically like compliant gears, except instead of all the rubbing and friction in the gears and all the issues that come with rigid gears, it's largely sidestepped. The one downside is gears can keep rotating forever, and these have a finite range. So I encourage you, this design was inspired from the most ancient toy known to mankind, which is a Jacob's ladder toy. And you basically get, they were found in ancient pyramids and stuff. Basically, you get like these wooden blocks, and you get these ribbon straps, like the Flexure blades there, and you stack them together in alternating ways, weave them through, and they do a really neat thing. So I encourage you to click on this link. I'm not going to do it in the lecture, but click on this link, and you will see how Jacob's ladders work, and they're kind of mystifying. Okay, so I said these kind of joints are used in robotic joints and all kinds of things, but my advance to this joint was I use them within architected materials. So you can, if you make lattices of these things, regardless of their shape, whether they're circles or circles of different sizes, or peanuts or ellipses or squares or mixed shapes, rectangles and circles, or aperiodic different shapes, or even 3D, you can make multiple layers and assemble them together, single piece layers, but assemble them together such that they achieve very interesting kinematics, sometimes 1 degree of freedom, sometimes many degree of freedom. And there's an interesting paper on that if you want to see that. Okay, so another application is flexure couplings. Okay, so again, in reality, nothing's perfect. You'd love to attach, say you want to attach a rotary motor onto some shaft, if you perfectly aligned it, then everything would be fine. The problem is you can't perfectly align things, so if you rigidly attach this, there would be some kind of stretching or shearing that would be cyclic. So as you turn the motor on, it would load the shaft of the motor in ways that would be very damaging, and it would fatigue it and it would break the motor. So what people do is here's a rigid coupling. As a result, you ground the motor, you ground the shaft on the other side, and then you have a cylinder here, and you cut slots in it, and you put these pegs through this shaft and the peg through that shaft, and then there's some slop in there, and so it can accommodate the misalignment, and all it will pass through is the torque, and all the rest will be taken up in the slop. Problem is they clatter around, which generates friction, which makes them inefficient and everything. It's nicer if you can just use a flexure coupling, a single piece that can deform to join the two directly. A single piece, no clatter, no rubbing or friction, and can still pass the moment while accommodating imperfection. Okay, this is another, this is an overrunning clutch, also designed by Larry Howell. And the way this works is, you imagine this is fixed, this kind of ratchet mechanism, and this outside spins. I think I have a video here. Okay. Yeah, let's see. Okay, so you can see that spins, and it can go one way. And so let's go back here. It can go one way, it can go this way without catching. And again, if it goes fast enough, centripetal force will pull these away so it doesn't make the annoying clicking sound. But then as it slows down, it starts ticking. And then if you try and go the opposite direction, it'll catch on this. So it can only go in one direction. Okay. And again, that was designed by Larry Howell's group. Okay, so another neat thing, application of compliant mechanisms, is they can be used to achieve multi-stability. So this is a, you look at this switch up here, this is a rigid mechanism, but they put a spring in there. And you can imagine it's stable in this state, and then you tick this switch up, and rotates around there, and this will tick down there, and in the way to lifting it up, this spring becomes very unhappy, a bunch of energy stored in it. But once it gets over the hump, it'll snap to the other one, and the spring will relax. So you can see it's a switch there. There's two states of happiness where it stays put, and it takes a force to make it unhappy to get it to the other state. It's kind of akin to if you had an energy well, or imagine actually just a hill, and you drop a ball. It's very unstable up here, and with any perturbation, it'll either fall here or fall here where it will be stable. And if you want to get that ball to the other side, you have to put energy in to get it up over, and then it'll fall to that state where it'll stay put. Well, compliant mechanism, this is a single piece compliant mechanism, and it's stable in this state, and then I can take it and pop it down, and it'll be stable in the state clicked down. And if you ever get to play with these things, I mean, they're very satisfying. They tick to these different states, and it makes this very happy, satisfying tick where it stays put. This is an example of a bistable mechanism, but there's multi-stable mechanisms all over the place where they can tick to many different deformed positions and stay stable. These are used in nature all the time too, by the way. Anyway, you'll see a lot more about this in my YouTube channel. Okay, so another area is lamina emergent mechanisms. So, right, so it's there's a lot of planar fabrication approaches. Usually, most approaches you can only cut things out of a planar sheet and then assemble them. Well, one trick is, and of course 3D printing disrupts that, but 3D printing is relatively new. It's advancing fast, and it can't do everything. So sometimes it's still beneficial to be able to make things out of planar sheets and assemble them, but the problem is, say you don't want to assemble them. Is there a way to cut something out of a planar sheet and then deform it in place? So this is like a light switch. This is cut out of a single piece, again by Larry Howell. This is all Larry Howell stuff. And then you can deform this in place, and it creates actually a bistable mechanism. This is actually literally a light switch that's stable there and stable there. Okay, so he made a bistable mechanism that came from a single planar cut piece that was assembled through deformation. That's a lamina emergent mechanism. Okay, so this is a great 4-bar example where out of a single sheet you can cut and then lift the whole 4-bar out, and it uses these torsion joints that can deform huge amounts without yielding. So you can get kind of a 4-bar there. This is a classic lamina emergent mechanism. Larry was able to make some really neat, this is particularly useful on micro scales when it's very difficult to make things and assemble them small. And most of the approaches in the microfab, the clean room rely on planar or at least 2.5D, 2D or 2.5D approaches. And so what he was able to do is make, use these approaches that are planar 2D, cut things and then deform them up into mechanisms. And this is a mechanism where he was able to put a cell in the middle there and then poke the cell with some DNA or whatever he wants to put in the cell with this sharp tip. and these guys pop up and hold the cell in place and everything. There's a great Veritasium video about compliant mechanisms where they show this working that features Larry's lab. Okay, so similar to this concept of taking planar things and deforming them to make a 3D shape is origami. Origami is essentially the art of, it's basically an art that leverages compliance. You basically take a single sheet of paper and you deform creases into it, permanently damage the paper, and actually deform regions of stiffness in the paper. And you can continually do this to make very compact shapes that can deploy to do some interesting things. So, you know, this shape can be wrapped up in a nice cylinder, but if you pull the edges, everything opens up. And NASA used this to, you know, you fit these things into tight cylindrical rockets, and then you release them, and by rotating the centripetal force or other actuation means giant panels of solar arrays can unfold using origami. Origami is great because it can be extremely compact and it can be lightweight, both of which are things that are very desirable for space applications, right? Because the weight of something in gold is how much it costs to fly it to space right now. We need a disruptive way to get things into space. But for now, right, weight matters an awful lot, and compactness matters. So origami is a big area in space, but there's many other applications for origami. Kirigami is another art form. Kirigami is basically origami, except you're allowed to cut the paper too. So you don't just deform it, a single sheet of paper, you can put cuts in it. And this allows you much more freedom. If you can cut the paper and assemble it and deform it, then you can get really crazy deployable structures that can be flattened to a super compact planar sheet and then open up into complex 3D structures. So you can see here, these are some beautiful kirigami works, and you'll see these in pop-up cards and all kinds of things. Okay, this is the last one. So that's a pretty cool structure there that can pop up out of a single planar sheet. Okay, so let's talk about advantages and disadvantages of compliant mechanisms. Okay, so let's first do advantages. Okay. So first of all, you can see this is a crimping mechanism. It looks a little weird because it's showing only half of it. It's symmetric around this line. So imagine all this, symmetric. And you can see this is a traditional crimping mechanism made of many different parts. It's assembled. They even threw a spring in there, just your common coiled spring. But there's a compliant version, and this is also symmetric. You can make the entire thing out of a single piece and do everything that the traditional crimping mechanism does. And so the first advantage, you can reduce part count immensely. Instead of having tons of parts, you get much fewer parts with compliant mechanisms often. Okay. As a consequence, they're much easier to fabricate and assemble. Oftentimes they don't even need to be assembled. They're monolithic, meaning a single piece. And if there is assembly required, it's much less, almost guaranteed. And oftentimes you can cut them out of a single planar piece like lamina emergent mechanisms. And if you need to make them 3D, you can deform them in place. So anyway, they're much easier to fabricate and assemble, much fewer part counts. As a consequence, they're much lighter weight. Remember, materials that can deform large ranges and are low, that are compliant tend to be less dense, so they're lighter weight. Right. So they're just lighter weight, which also means they're cheaper to transport. All three of these things cause reduced costs substantially, and everyone cares about money. So if you want to go cheaper cost without sacrificing quality and oftentimes improving quality, you can make things compliant. Okay, so you reduce pin and sliding joints, okay, which means you reduce friction and wear. Not only, they all involve assembly, but anytime you have contact joints, you're rubbing, you're creating heat, you're creating wear and particulates, and you can get rid of all that. You can reduce friction so no heat is generated or minimal heat. There can be internal friction with deformation, but minimal compared to sliding joints. and they can never wear down, okay, and not produce dangerous particulates that gunk things up and jam things. Okay, so they reduce maintenance substantially. Right. So if you have just a single part, and something breaks, it's very clear to see where it broke, right? But if you have many different parts, and maybe they're generating particulates, one part's getting jammed, it can be difficult to see, and it can be difficult to fix and replace and everything. So this becomes particularly clear when you try and find something that has the same precision capabilities as a compliant mechanism, which I'm going to talk about a little bit later. The competitors, like magnetic and air bearings, are way more complex, way more expensive, and way more difficult to maintain than just a single cheap compliant mechanism. But I'm going to talk about that later, so I'll save my my ranting about that. They can also store energy. So for this crimping mechanism, they had to put in a coiled spring in addition to the rigid parts to store energy in a desired way, deformation energy, and you get that for free with compliant mechanisms. They naturally deform and store strain energy inside. And so that can be a really good thing sometimes. Okay, they're also easily miniaturized or made really large, right? So one of my class projects was to design a foundation of a building that was basically a Flexure compliant foundation that could be adjusted with pneumatic actuators to make the building impervious to earthquakes, tune its natural frequency. And so anyway, flexures can be made giant, they can be made small, they're almost any scale. The equations, the physics, doesn't really change. Whereas, contact or sliding joints that do the same thing, guide the motions you want, they, on the other hand, have all sorts of issues when you get smaller. As you get smaller, instead of inertial forces dominating, you get surface and adhesive intermolecular forces. Van der Waals start mattering, electrostatic forces start mattering, and things start sticking and binding on small scale. So, if you want to make a micro motor, it's very difficult unless you achieve your relative motions using deformation. So flexures are easy to make on a small scale. And I'll talk a little bit more about that too later. Possibly one of the best reasons to make something compliance is to achieve precision. I came from Marty Culpepper's lab at MIT as the Precision Compliance Systems Lab, and it was everything about precision. Most super futuristic technologies that don't exist right now don't exist because we don't have the precision to enable them to exist. This includes all sorts of crazy, Star Trek, Star Wars kind of technologies that are totally achievable if you have enough precision. And I'll define what precision is and why compliance is good at that a little bit later. But that's, I have to mention that on the list of advantages. Okay, and there are many other advantages. Watch my YouTube channel to learn more about them. Okay, so as a consequence, you can, one way this class can change your life is as you go about living as an engineer, you will see tons of rigid mechanisms, like for instance these handcuffs. It's many different parts. There's all kinds of pieces in here to click these things together and pin joint together. And there was a company that actually used something similar to a handcuff to bind cords together. And so someone came along and said, well, why don't we just make a single piece part, injection molded, way lighter weight, way cheaper, and it can deform and click into place just using compliance and easily release to bind cables together just as well, if not better, for 1/100th the price. And so they totally put this company out of business. So you can do this. You can look around in your engineering life at just products and see, oh my goodness, I could make that way cheaper, way better if I make a compliant version, go make it and put them out of business. These are name tag clips with springs, and also particularly look for things with springs inside. A lot of times people don't know about compliant mechanisms, so they just design a rigid mechanism and put like a coiled spring inside, which I don't think should be classified as a compliant mechanism, even though technically it's got a compliant part. It's a rigid mechanism with a coiled spring is what it is. But if you ever see a mechanism like that, you can almost certainly replace it with a compliant mechanism version where the whole thing is a single piece. So you know, I went to a conference that was trying to be more energy efficient and save the planet and everything. They decided to make, instead of giving everyone name tags that were made of all these different pieces that were expensive, they just made a